Hello, everyone, and welcome to the Automation Village breakout sessions. Right now, you're watching the power stream. We also have a water wastewater stream and an oil and gas stream. So if you're interested in those, check back to the invite. Today, we're going to have three different presenters. We're going to have Scott Coleman from Owl Cyber Defense speaking to us about data diodes. We're going to have Jeff McKinnon from JMK Engineering talking about central monitoring, utility protection, and control systems. And we're also going to have Gautam Ashikumar and Jeremy Blair from Schweitzer Engineering talking about arc flash mitigation. So first up, I'm going to have Scott Coleman join me. So Scott, if you're available there, I see you just got your camera on. How are you doing today, Scott?
Very good. Thanks for having us on today.
Great. Yeah, I'm glad that you guys could join us. It looks like we've got a number of people. People keep streaming in here. So, Scott, today you're going to talk sort of briefly about data diodes. And I shouldn't say briefly. I guess it's not too brief. We've got a 40-minute presentation.
Right.
So, yeah, you're speaking today about data diodes and isolation, but also realizing that people have that need to still bring in data from third-party sources and other things, so they can't just completely block traffic. And it's about managing that. Is that correct?
That's right. Exactly. It's how you instill security while allowing sort of business operations to continue.
Right. Okay. Fantastic. And for our viewers today, if you guys have questions, then we'll have a in your console there. You should see a little Q&A button. It's got like a little bubble window for that chat kind of box. So it's different than the chat window. There's a Q&A button there. So if you submit your questions into the Q&A, then at roughly 40 minutes past the hour, I'll jump back in. I'll grab sort of control from Scott, and we'll go back and forth on some of the questions, and Scott will be able to answer those. So it'll be the same format for all of the different presentations today. So basically, we've got those three presentations. It's going to be about 40 minutes per presentation. Then we're going to put some time into answering your questions. And then we're going to kind of give you a little bit of break before we start the next session. So Scott, whenever you're ready, feel free to take it away.
Great. Thank you very much. All right, so before we get started, I'll probably just give a quick introduction about OWL. For those of you that aren't familiar with us, we've been around for 20 years now. We actually started in the critical infrastructure and DoD areas. The technology was primarily used by the U.S. government originally, and then since then, we've expanded into many other solutions across with today speaking about power generation specifically. I guess one thing I'd like folks listening in today to take away is that the technology we're talking about is technology that's used to secure some of the most important networks in the world. Those used by our DoD and intelligence agencies to support a number of different types of missions. It was well over 10 years ago now that we then took that technology and brought it into critical infrastructure, first in the nuclear power industry, and then into oil and gas and power gen and water, wastewater, et cetera. So it's quite a number of use cases that we've expanded into over time, keeping that core capability and level of security that the government has come to expect over the years, and now we've brought it to critical infrastructure. We offer a variety of solutions, ruggedized solutions, as well as standard 1U rack solutions, all certified around EAL4. We've done third-party penetration testing, etc. And we are an all-U.S. supply chain. Manufacturing and development is all done here in the U.S. We're actually based in Connecticut, and we have a facility in Columbia, Maryland also. We also have distribution partners internationally in Europe, Middle East, Asia, Canada, while serving both sales and support and installation services. Okay. So I'm going to make an analogy here, or a parallel, I guess, not an analogy, between the safety and security that we're really looking at for ourselves in terms of protecting ourselves against COVID-19, and then how that relates to securing your plant against computer viruses. So we're looking at CDC today, recommendations from them, talk about physically distancing yourself, eliminating unnecessary interactions, using one-way delivery of goods. So think Uber or a driver dropping off things at your house, and then moving in one direction in grocery stores and layers of protection. Now, for years, the DHS has been giving us very similar guidance for how to protect our equipment. And this is something we've been talking about for a while. There's actually a white paper that they have published, which I'll reference here in a couple of minutes, but they've been talking about the exact same thing: physically segmenting networks and devices, just like you're now segmenting your person, eliminating unneeded connections, using one-way transfers of data, not unlike a one-way delivery of goods, transferring data out of a plant, i.e. like moving groceries, and using defense in depth. So the same way you're using gloves and masks, etc. Defense in depth is always a great strategy. And then, of course, most everyone at this point is doing remote monitoring or, managing their life, their jobs, etc., remotely as much as possible. And we all know that safety and security is never convenient, but there's always some things that sort of make it less useful and harder to implement but it's the only way to be safer and more secure. And that's sort of, I think, at the top what we talked about in terms of putting something in to allow business operations, but in also inserting some security there. Okay, so next slide, 583. This is the average number of external connections that folks have in and out of their facilities. And really, when we talk about trying to reduce threats or increase security, it's about managing that number, trying to reduce it. And I'll talk about how the guidance that the Department of Homeland Security has given us and how that relates to this. Now, some of the reasons why we have so many connections and why we're continuously making more holes, because you got to think of each connection as a hole in your network, right? You've got a perimeter, you're defending that, and it's the holes in that perimeter where you have vulnerabilities. And those are the things that let you conduct business, but also the things that are now creating threats against your network. And there's good reasons why those holes exist. Obviously, more and more folks are putting stuff out into the cloud for storage, for processing, for monitoring, et cetera, all kinds of good reasons. The Internet of Things and creating devices that'll talk to each other. And then, of course, digital transformation, which is going on. So all these things are great for improving connectivity, communications, et cetera, but also sort of horrible for keeping a secure platform. And so we're going to walk through how you can still support these things, but stay secure simultaneously. Okay, so if you look at what that might look like in terms of a diagram or a picture, this is the idea of how do you do remote monitoring without remote access. And if you think of products like Dream Report, where you can do monitoring remotely of what's happening inside your facility, the premise of people usually think, oh, remote monitoring, that means I'm reaching into a plant and getting data I'm pulling out, and now I have this great dashboard that all my folks can view. The problem there is that you're reaching in to grab the data to display. And what we want to do is talk about doing the ability to do monitoring remotely without having to have people reach in and grab data. So all of these are two-way connections. You can see here the arrows pointing in and out, whether it's your cloud or vendors or remote monitoring, your logistics providers, disaster recovery, all kinds of really good reasons why you need to share information and have those connections in and out of your network. Okay, so the third-party connections, I think we just sort of covered this: cloud services, software vendors, IT support, HVAC, et cetera. A lot of these you can pick out and say, hey, yeah, I heard about a threat, right? That's the HVAC one is a great example of what happened at Target in terms of someone coming in through a hole in their outside network, not having the proper segmentation to prevent that from that penetration for spreading across into other platforms, other networks, and then sort of leading to a significant threat into their overall systems. people always ask, okay, so when you work with data diodes, are you limited to the amount of data, types of data? No. Historians or SCADA systems, SIM data files, syslog, video. There's a whole range of data types that are supported across diodes. Okay, so the Department of Homeland Security, what is their, they actually have 7 strategies for defending industrial control systems. And those include what application waitlisting, configuration patch management, reducing your attack surface, defending your environment, managing authentication, implementing secure remote access, monitoring, and response. The 3 that I'm going to focus in are number 3, 4, and 6 there. Those are the ones where they actually explicitly mention in their strategies data diodes and how you can use one-way flow of data to implement those strategies. So those strategies come down to basically these 4 bullet points here: reducing or eliminating connections in and out of the network. So that's back to the 583. How do we get that number more manageable for us? And not by disconnecting data from folks that do need it, but potentially limiting ones that are no longer valid, no longer in use, or just aren't necessary anymore. And for those that you do or are unable to eliminate, that you still have, right? So converting those from those arrows, right? Each one of those is a 2-way connection in and out in the previous diagram. How do we convert those to 1-way out of the plant? I.e., how am I going to move that data, still share that data, because those are all valid reasons why you would share data, valid users and consumers of that data, which I need to provide to them. But how do I do it without having that remote access? How can I do remote monitoring without remote access? And that's really by converting it to a 1-way out of the plant. They also go on to say that if you are moving stuff into the plant, let's say a software patch or an update, how do I do that in a secure way? And again, the recommendations make that a 1-way transfer into the plant. We need to apply potentially virus checking on that. You can do checksums against that to make sure the patch that you're sending matches the original manufacturer's patch through a checksum. And there's multiple guards that you can put in place to make sure the information moving into that plant is secure. Do it through a 1-way. That way you know there can be actually no leakage out through the plant through that 1-way in. And then for those remaining connections that absolutely have to remain 2-way, and we all know that there's some of those, right? You can't convert everything to 1-way. I caveat that a little bit because the nuclear industry has actually done that, coming out. All of their connections are 1-way out. But again, it makes it's a level of difficulty that's added when you do that conversion. So what we're really trying to do is say, how can we make that as easy as possible? And the easiest way to do that is to have some of those that we know need to be 2-way, to leave those as 2-way. A great example is maybe a cash register, a point of sale or something. You're not going to convert that to 1-way. You need to go out and do checking of balances and debit cards and all those kinds of things. So there's clearly examples of where you need to maintain 2-way connections, and you'll never get to 100% 1-way. So let's go a little bit further into those and think about what a diode is versus what software. You look at the sort of spectrum there, you see data diodes always all the way over to the far right, and that's the most secure thing. Air gap being a point in time where you actually physically completely disconnected, and there's no communications whatsoever. We've actually had people say to us, well, you know what? Data diodes are actually even more secure than an air gap, because what you're doing is allowing business connectivity to still occur, and therefore you're reducing the possibility of people trying to bypass it. So if I go full air gap, now I'm tempted to take a hard drive or a floppy drive, I'm dating myself here, a USB stick or something, and carry that into the plant and pull information off of that. So we actually, by putting a data diode in, allowing data to flow, but securely flow back and forth, then you actually end up being more secure than air gap because you're reducing that temptation to do it manually. So diode is hardware-based. For those electrical engineers out there, right, they all know what a diode is, and that's how I can usually tell when someone comes up to me at a trade show and they say, hey, I know what a diode is. So a data diode sends data in one direction only, and that, yep, exactly right. And then therefore, the premise of that, it is hardware-based and not software-based. Most of your software applications, your software security, is based on some kind of configuration. So people say, well, yeah, I've got my physical firewall. Yes, it is. And it does run on a piece of hardware, but it's based on configuration. It's based on settings. It's not based on the physics. So on the next slide here, we'll talk about the actual device and what it looks like. But to summarize, software is based on configurations. Zero-day exploits can get across them. We see that. We see people getting hacked all the time. It's not because they don't have firewalls in place or good methodologies. It's just that you can't completely isolate that those kinds of exploits through a software configuration. Malware and ransomware, I'm going to talk about that in a minute, how that gets prevented, but obviously software is susceptible to that. And to keep your software-based cybersecurity products up and running and performing the way they need to be, there's a lot of ongoing management that needs to take place. With Diodes, the physics enforces the security. That never changes. You can't replace that. You can't do something about it. It's unhackable, and I'll explain that in a second. And is invulnerable to malware. And as I go through explaining the diode and the components, I'll explain why that's true. And once you get it set up and running, there's really little to no ongoing management. So you think about your cable modem at home. Once you get your cable modem up and running, there's really nothing you need to do to it. Data's flowing back and forth across it. With a diode, it's very, very similar. You get it up and running. You know your data flows, and once you've got your data flow stable, then you basically nothing you really need to do to the application or the platform itself, unless you at some point in the future wanted to add a new data type, which in itself is actually very easy to do also. Okay. So looking at the data diode itself and how it works, I think it's worth spending some time here to understand this because the concept is new to folks, and I think the basic concept gets across pretty easily, but I think it's sort of digging into the secret sauce that makes how it works is worth discussing so people understand how maybe some of those use cases that'll be shown later on apply. Or obviously coming up with your own, I apologize, coming up with your own use cases. So at its prime level, at its most lowest basic level, a data diode is constructed of a send side or a transmit side and a receive side. And in this case, the transmitter is an LED that sends light over a fiber optic cable over to a photoreceiver on the other side. The data flows as light across the data diode from the sending LED to the photoreceiver, and then it goes on its way. I'll expand on that in a second. What's interesting here, unique here, sort of the aha moment for folks, is that with a data diode, once that on the receive side, I have no LED to send light backwards. Now, in a normal fiber optic cable configuration, you would have light being able to send both directions back and forth. But in a data diode, there is no LED to send light backwards. And on the inside, receiving side, what was originally the transmit and send side, the side there on the left, where we have the red LED light, there is no photoreceiver. So you literally can only send light in one direction. You can't send light back in the opposite direction because the physical components to allow light to go backwards or go in the opposite direction don't exist. Therefore, that is the basis for the claim that it's unhackable. If I cannot move light or data in through the device into the network, physically impossible for someone to hack because I can't go backwards. I can't send light backwards through components that don't exist. There's no zero-day exploit that you can apply to the configuration to now magically have the components that are missing, recreated. There's no malware or anything else that can be applied that was going to somehow be able to bypass the physics. The device is physically separated literally down the middle. You have a power supply on one side, you have a hard drive on one side, you have communications on one side, and you have a CPU on one side. And that would be on the send side. On the receive side, you have the exact same thing: its own power supply, its own hard drive, its own communication cards, and its own CPU that's doing processing. And the only thing in between the two is the fiber optic cable connecting from one side to the other. So really straightforward. Data comes in from the left, goes across the diode to the right, and off it goes. The obvious question, and the question we get the most, is, okay, I get that. So maybe if I'm sending a photo or something or a file, I get how it can go one way. But geez, all my networks are two-way. They all work in a two-way fashion. There's concepts of flow control and acknowledgments and all those kinds of things. So how can I use the diode in those kinds of networks if it's just sending things one way and I'm not acknowledging information? So I'm going to dig a little deeper into exactly how this works to try and answer that question, because it's the most obvious question. And it is important to understand, because that's really where the secret sauce lies. That's where what makes this thing work. Basically, anyone could build a simple diode that's sending light in one direction, right? While you have to do that right and do it well, that's not the components. It's important in terms of making this a tool and a product that can be used in networks today to make it basically invisible to other users that there's a diode sitting in between. So what we run on both sides is a proxy. So I'm going to take TCP/IP as an example. TCP/IP allows you to send data. TCP/IP expects acknowledgments and sort of X on, X off, and flow control, and those kinds of things as data is sent. So if I'm currently sending data from source side on the left to receive side on the right without a data diode, the source side would contact the receive side, saying, hey, I'm going to send you some data. Receive side said, yes, go ahead. I'm ready to receive your data. Source side would send the data over to receive side. He would receive it, acknowledge it, etc., and we go on from there. So source side and receive side sending data back and forth to each other, acknowledging that the transmission of data. Now, if you put a diode in there, obviously source side can send stuff to receive side, but he can't send it back. Therefore, I've now broken my ability to support TCP/IP because that return acknowledgement doesn't exist. So what happens instead? We set up a proxy. You'll see it there, internal proxy on the transmit side next to the source. The proxy now becomes the new receive side. So he communicates with the source side saying, hey, you need to send some data. Great, I'm ready to send it. Or no, I'm not. X on, X off. Slow down some data, or I'm ready to receive additional data. So they communicate. They talk to each other. The data gets sent over. Source side is happy because he's talking his normal two-way connection. So think source side is any device in the network, a SCADA system, a historian, even a simple file transfer, whatever it is, that information, that part of the network is happy because he's continuing to talk his sort of native tongue, if you will. The proxy takes the data, terminates the session in essence. And then what we do is we take the payload only. So the payload from those packets is pulled out, and we send the packets of that payload, the payload from the packets across the diode to the other side. On the other side, there's a new proxy that picks up those payload and reconstructs them into the original back into a TCP/IP session. He knows the IP address of the receive side and says, oh, okay, this payload came in through this channel. I'm going to then map it to a TCP/IP session because that's where it belongs. So that's what it needs. That's what the receive side is expecting from me. And he initiates a new TCP/IP session on the receive side. They're talking two-way, everybody's happy, and away we go. So you end up with a two-way connection conversation on the left side, source talking to proxy, the data diode moving the data across, the payload only across to the receive side proxy, and then he communicates with the receive side again in a two-way fashion. So we're sort of sitting in the middle, one-way transfer across your domains, across your network boundaries, across your segments. So whether it's a very large segment, maybe a whole plant, or maybe it's just a small one, guarding a turbine or something like that. You can put the diode in front of it, speak your two-way communications on either side, get your payload across, get your data across with complete confidence and guarantee that no one can back in through the diode and into the plant to mess up things on the inside. Because that's what, really, that's what we're aiming for, right? We're aiming that no one can get into the plant, disrupt operations, but we need to share that data out to those external parties. So that's how it works. It needs to be fast. It needs to have low latency. So we actually use the ATM protocol, for those of you who are familiar with that. That's a high bandwidth, low latency protocol that's used by the phone companies for voice and data. So it gets those payload packets across very, very quickly. We're talking less than 7 milliseconds, so 7/1000th of a second across, basically imperceptible to the human eye. And we can move lots of data across that, scaling up from very smaller systems up to very large 10 gig systems. Usually in critical infrastructure, that's not necessary. Usually it's a very small amount of data, whether you're talking about something like a single turbine providing information, maybe a solar panel array, renewables, up to a full historian replicating hundreds of thousands of tags, in which case you would need a higher end solution, but the solutions scale to meet those demands in terms of data that's being moved across, back and forth across the platform. All right, so I hope that answers some questions. I hope that people understand how this works. The other question we get a lot on this is, okay, you sent the packets across. How do I know that they got there, right? What's my guarantee that the data actually got there? Because normally with a two-way conversation, you're going to do packet acknowledgement. So 2 parts to that answer. First part is we're literally moving the data inches. It's going from one side to the other, and it's moving literally inches. In some of our smaller platforms, it's not even going an inch. Very, very short distance. There's no routing in there. There's no switching in there. There's no network congestion. We're not competing with other traffic. It's our own traffic, purely point-to-point, hardware fixed across. So there's absolutely no reason why you would ever drop packets. And I can tell you we have thousands and thousands of deployments, and that's never an issue. And on the other side, the receive side is actually capable of tracking that it's getting packets in the right order and it's getting things that it's expecting, and it can do checksums and things like that. So the onus becomes on the receive side to make sure he's not missing stuff, rather than on the send side to guarantee or to check and see if the receive side did get it. So the checking is done on the receive side rather than on the transmit side. And then the obvious question there is, well, okay, if something's missing, what happens? And then the receive side would send up alarms and say, hey, I'm not getting everything, or something's happening. And it's typically what happens is more data is trying to be sent across a platform that hasn't been scaled properly, or an incremental license is needed to allow more data to go through. Another data source was created, or maybe something is refreshing much more rapidly now than it used to, or something along those lines. And that's easy enough to change, increase the capacity, and balance it back to where it needs to be, so you're not dropping. Very rare that ever happens, but in the case it does, that is how it's addressed. Okay. So I'm going to keep moving here. I'm just going to give you a quick shot of this is actually our Diode product. So this is one that could be DIN rail mounted, for inside facilities. We have other units that are 19-inch, wide enterprise solutions. They all have the same functionality basically, and they scale up from a single purpose. This is a single purpose device, all the way up to multi-flow, multi-protocol, simultaneous. All of our solutions are a single box. There is no flanking service, no other devices that you need. It's just a single device here that can be used. All right. So use cases. So I'm going to start a little generic here first. We've got product deployed in water and wastewater solution environments, power generation, nuclear, renewables, hydro, fossil, etc., all using our equipment quite extensively. T&D, very extensive set of users using our stuff for sub. But we're also in oil and gas, upstream, downstream, rig refineries, petrochemical, transportation, financial services, manufacturing, pharmaceutical, etc. So lots of different use cases, lots of different customers using technology to protect their facilities, protect their segments, and still share information out. So we'll take a quick look at the first one here. So this is, and you'll see it's going to be very similar. There's not a ton of difference between the use cases because in all cases you're moving data from one area to another area, and it's really comes down to the type of data that you're moving and who are the recipients of that data. So in this case, we've got a turbine generating electricity. We've got folks at a remote facility, so that could be the third party, right? That's so maybe it's my equipment manufacturer. They want to get information around usage, cycles, how much time is being, how much operational time is being on the machine. And then maybe I have a remote monitoring facility wants to know how much power I'm actually generating. So two different source types of data for two different reasons. One is for my third party. He needs to understand for preventive maintenance purposes, how much the equipment is being utilized, and all the relevant information for that. And then for remote monitoring, maybe I need information to make sure I know if I need to increase my output, decrease my output, depending on the load across the grid, et cetera. And so the remote monitoring facility is getting much different information than my third-party contractor who's worried about maintenance. So all that data can go across a single diode, no problem. We do that all the time. The data is generated, and you could have the turbine generating part of that data. You could have some of the data coming from another data source. And sort of stepping back to the proxies we talked about before, what we would do is if the data type is different, then it may require a separate proxy, and so we can run lots and lots of proxies next to each other, managing data, different data flows and different data types. So a historian would have its own proxy, a TCP/IP connection would have its own proxy, a UDP would have its own proxy. But if multiple sources are sending different types of UDP data, they would all flow through the same UDP proxy, but as different individual data flows. So you wouldn't have to have multiple UDP proxies running simultaneously. Okay. All right. Moving on to a next case. This is a story of application. So I've got a fossil-powered power plant. I've got my Pi server on the inside. I've got end users out at HQ. They want access to that historian. And obviously this can be any historian. It really doesn't matter. This one comes up as just a use case that we see very frequently, where you need to get that historian information out of the plant and out and get it replicated. This is a gas-powered generation plant where you've got a gas turbine, and it's generating, again, similar to the other use case we saw here. The difference here is they've actually got connected to a modem. So lots of times we'll see that I won't say lots of times. There are occasions where we've got some very old equipment in the field that folks need to connect to, like a modem. And this could be a cellular modem. This could be dial-up modems. We've actually support both. It doesn't really matter to us. Because if you think about the diode is sitting at the brink of the edge of the demarcation point between the gas plant and the outside world, the internet, if you will, whatever network connectivity is out there. And the data diode doesn't care what it talks to. So it can send data to a modem, right? As a cable modem, dial-up modem, whatever. You're still getting the data across. And once it gets across, and then you can transmit it via whatever means you want to that end user out there. Same is true on the inside. Folks ask, hey, if I have some kind of wireless technology, does that work with the diode? Absolutely, right? I mean, all wireless technology hits a antenna or receiver and then becomes wired data pretty close to where your wireless device is. Wireless makes it convenient, but once it hits something land-based again, then that data can then flow across the diode, and that would be your output source going across. And so you could have your wireless on the inside, you could have cable modems, dial-up modems, cellular modems on the outside or inside, but they can all traverse the diode. So it doesn't really matter. It's just data, and it's different transfer and receive mechanisms that need to be used there. This is a substation. We've got operations data, historian data, SCADA data that all needs to go across. Again, going to different facilities. Maybe it's my ops center. Maybe it's our OEM. But again, it doesn't matter if there's one source or multiple sources of data. It can all be concentrated across the diode and sent out simultaneously. And then this is sort of the tricky one. This is the last point that the DHS mentioned, that for those, you may still end up with two-way communication requirements after you've done your one-way out and your one-way in. And as the quote here says, is out of that same strategy report. If bidirectional communication is necessary, use a single operation port, open port over a restricted network. And so that's what we've actually done with this Recon product. And so when you get to a situation where you do need to maintain a two-way connection, what you want to do is lock it down and make it extremely difficult to do anything but that one communication. And so Recon does that. It locks down, uses a single port. The analogy used here is an airport analogy. So if you think about cyber or security at the airport, when you go in to the airport, they scan you, they scan your bags, they scan your ticket, your ID, etc. You go in, you fly wherever you want, and you come back and you land. You don't go back in through that same one-way gateway, in essence. You go through a different way outbound channel, and where there's typically a guard sitting there, and there's a line. Once you cross that line, you can't go backwards. So two one-way paths. One going in does a lot of scanning, a lot of verification. The one way out, physical blocking, and they're working autonomously, have nothing to do with each other whatsoever. But data is making it's round trip. It's TCP/IP round trip. And as a passenger, you can go through security, make a one-way round trip, and on Recon, you can do that same one-way trip around. So that was a little funky. People end up having a lot of questions about that one. But it works great because we've seen how it works supporting remote command and control, remote help desk operations, voice over IP, file transfer, where you need some kind of acknowledgement at the end, SCADA system work over it, database replication, etc. So lots of different use cases there if you're in a situation where you still have to maintain that two-way. Now, this is the last layer, I guess, is maybe the tier. One way in, one way out is the most secure, but when you need to go two-way, this is where you need to end up. Okay. So moving on, excuse me, to NERC SIP. So we do have a white paper, and I would suggest folks that are interested in to grab that. It's called Addressing NERC SIP Compliance. It's in the resource library at our website, alcyberdefense.com. And the most relevant part really around data diodes and how they play into NERC is in section 5. Creating a strong electronics security perimeter, and that's really what we've just been describing, is how you build that strong security perimeter. Disconnecting from the outside, and again, when you have a diode in the middle of there, you're disconnected. Limiting or eliminating the use of routable protocols. So when you think about, I was talking about the diode itself, using that ATM protocol to move stuff across, that's a non-routable protocol. It's going point to across, none of the IP information, none of the header information, all that is stripped, because remember, we're just moving the payload across. So when we do that, we don't expose any of the internal IP information, the routing information, etc., to the outside world. And so one of the things what that helps with is malware. So if I had malware got loose inside my plant for some reason, someone made a mistake and plugged in an infected USB drive or something like that, because malware likes to phone home or do other things or replicate itself, because we're stripping off everything except for the payload, and it's a point-to-point connection, And because when the source comes in, it's mapped to a specific destination, you can't go any other way anywhere else. And because you have no control of where those points are, basically you create a inert malware. It could infect internally or a ransomware, but it really can't get out into the wild or go from plant to plant because of the diode in there, and it's stripping out and just not using any kind of routable protocol. And then the last point they make is about forcing off traffic through an electronic access point. Obviously, a diode serves that purpose for you. In terms of, and this is again out of our white paper, there's part 1.1, .2, .3, .4, and .5. In the white paper, we break that down, showing what the requirements are, what it's applicable to, and then the OWL sort of diode solution for that particular requirement and how it may be used. So another sort of set of use cases here in terms of, here's the requirements, how do you serve that, satisfy that requirement within by staying in compliance in using the diode technology. Okay. The last slide I had here, if I remember correctly, is just some of the more commonly answered asked questions, I guess. We have a chat session, chat capability on our website. We're answering questions all day long on our folks. And so I'm just going to go through a couple of the top ones that folks ask. We see there quite often. Evaluations, proof of concepts. So we know that this technology is definitely new to some folks, or maybe they have something else in their network and they'd like to try an OWL solution for the first time. We do provide free evals and proofs of concept. So we can definitely tell you, what we've supported in the past, the different types of data, et cetera. But if you feel you've got something unique or different, or you just need to test everything in your lab before you put it into production, we get that. And so we do support evals and proof of concepts for folks. We'll send equipment out, help you get up and running, do your testing. And when you're completed, you can either buy the equipment if you want to move forward, or just return it to us for no fee. Give you basically a 30-day window to do that. Ease of installation. Folks have sometimes comparing what we do to some of the competitors in our space. And we've heard quite a few stories about solutions taking weeks, months to get up and running. I would say that most of our customers install this equipment themselves. So it's probably 90 to 95% of customers. We ship them the product, they get it up and installed and running without us, not having to go on site or anything. We do offer training classes for folks, and we do recommend them. And we do offer installation services, but the bulk of our customers are able to get the equipment up and running on their own, usually the same day it arrives, kind of thing. So this is does not need to be a complex installation. The other thing that people ask us, in fact, I'll go back to ease of installation for a second. We actually had a customer that ran a contest internally with a new Dioda product that I showed you a couple slides ago. And they were able, I think the fastest time they could get it from sort of out of the box to up and running, passing data, was less than 5 minutes. So extremely fast if you really put your mind to it to get it up and running. So ongoing management and configuration. For folks familiar with firewalls and what it takes to do with that, as I mentioned earlier, it's just sort of the cable modem model where once you get it up and running, once you've identified your flows, like this is a TCP flow, or I need to replicate my historian, or wherever it is, and once you get that up and running and it's stabilized, again, usually in a matter of hours, what we do is we'll install, leave the premises, let it run overnight, come back the next day, make sure you're all good. And that's sort of the extent of what installation takes. But once you've got it to that state where it's up and running, I've had multiple customers come to me at trade shows and say, "Yeah, we've had it up for 2 years. We had to go find the the password on the little white yellow sticky note somewhere, because we hadn't logged into it, because there's no reason to. This, as opposed to customers we've talked to that have actually done internal audits, and they found that they failed their audits because they didn't, not because the equipment didn't work or properly, but because basically everyone has their day job, right? If I've got multiple industrial firewalls or something scattered around my plant, and they're all doing their thing, but I need to constantly patch them every Tuesday or once a week, or every 2 weeks, or whatever it is, whatever that iterative cycle is. The problem we found was that they were all out of date. They didn't have the current, most recent update. And if you don't have the most recent update, then you can't count on that technology the way you should have. So it requires a lot of ongoing maintenance. And so with, obviously with data diodes, as I described, the security is in the hardware, not in software configuration. And therefore, once you get it up and running, you stay secure, and there's very little reason to ever have to do updates or patches to the platform. Another question that comes up quite often for us is number of devices, and that is a single box. So all of our solutions come in one box. There's no flanking servers, there's no transit module and receive module and other components and things. It's either a 1U 19-inch rack mount solution or one of the vertical ones I mentioned before. And at the last question here I'll touch on is price. And folks usually ask, where do they start? Where do they go to? And at scale, our new Dioda product, single purpose, actually can start down around $3,000 to $4,000. And then products scale up from there, in that 10 to 15 range is typical. And then it goes up from there depending on bandwidth. So that's it, everything I had. Yep, great.
That's we're just coming up just a little bit past Q2 here, so I'm going to jump in. I let you kind of carry on. Your questions were fantastic because I'm sure that answered a lot of things people are wondering. I do have a few questions from some others here.
Great.
And while we're answering those, I'm just going to throw up a slide to show anybody else who may be looking to ask a question where the Q&A button is here. So first off, we've got Paul, who's asked, can we get a copy of the presentation? So Scott, do you have something like a publicly distributable version of your presentation, or?
I do. So I can either, I can provide it to you guys if you want to distribute, or I can easily email it. This one is not very large. I think it's less than 8 meg. So it usually gets through anybody's email,
Right. Okay.
systems.
Did you want to read off your email, and maybe somebody who's looking for the presentation can?
Sure. Absolutely. So it's first initial S and then last name Coleman. So S Coleman, Coleman at owlcyberdefense.com. And you send me an email, I'll send it back to you. Or just, if you forget it or whatever, just come to our website and jump on chat and just say, hey, I'd like a copy of the presentation from today's webinar.
Perfect. And for anybody wondering, we are recording the webinar today, and those recordings will also be made available to all the attendees. So you should be able to watch something, especially if there's something conflicting in another stream, you'll be able to go back and see everything there. Next question is, in general, do all data diodes from any manufacturer come with an internal proxy for TX and RX side, or is that something data diodes would require additional servers which will have to be configured as proxies?
So I'm reluctant to talk about other people and their products. But yeah, there is. I don't know how other people run their applications, and we've seen conflicting information, and I've heard customers describe what they've been told from competitive products. There should be some kind of proxy to do conversions. Many times, and this gets back to that question about single box, multiple boxes. So most of our competitors that I'm aware of all have multiple boxes. They run their proxies on additional pieces of hardware. We run all of that on our single device that I showed you. So we've had cases where we've gone in and competitive situations where the customer has decided to replace existing equipment with ours, and there's literally been 12 servers, there that literally get replaced by one of our devices. So I would say in general, most customers, everyone should be running some kind of proxy, because otherwise you're breaking some kind of two-way thing without a good resolution for how to handle that. And if they're not, then that may be why they require these additional servers to retransmit things many, many times to make sure it's all getting across, and then trying to stitch it all back together. Like I said, I'm making some assumptions there. I can't speak to the competitive products,
Sure.
but most of them do have these other flanking servers that they need for their solution.
Perfect. Yeah. Okay. So I've got another one from Paul here, and it
Mm-hmm.
says, "Is there a life expectancy of a data diode?"
Sure. So that's a great question. The mean time between failure on our products typically runs around 14 years. One of them, and so they're designed to go into the network and run for very long periods of time without having to build. These are not running on commercial off-the-shelf servers, that you need to be refreshed after 3 years or something. This is hardened hardware that is designed for industrial environments and designed to run for many, many years without having to be replaced.
Right. Fantastic. So
Good.
I've got one more question here, and
Okay.
then we'll give a few minutes for some other people to go in. Again, you should see the slide there with the Q&A button there, and Pete's Pete's big portrait. And so you click that button, enter your question, and then we'll take a look for it, and we'll go through that. So the last question here from Ricky says, "Is there any real case in power plant that you could share how data diode G/W work for IEC 61850
443.
power plant?"
Oh, 850. Okay. So we are doing stuff with IC 104 right now, as well as DNP3. We've tested both of those. They're in active evaluations, both in the States and actually in some of our international customers. I would invite a conversation around that, and we can find out exactly what you're doing. But yeah, there's a lot of activity around those standards right now. And in terms of supporting those, and we definitely have solutions architected, and we have proof of concepts running in the field today.
Cool, fantastic. And I'll just give a few more minutes here for somebody else to put in a question. So it's your last chance. While we're doing that, I thought the presentation was really great, Scott. Thank you very much for that. I was really interested. I was always a little curious with data diodes how things like the acts actually happen, and so it was
Sure.
great you answered those questions. Also, in my position, I guess I see a lot of things like recommendations for NERC SIP and other things like that. And it was one of those things where, yeah, when you were describing sort of how your product works and whatever, one of the things I often see is the recommendation that anytime you're basically crossing from, one network to another, there's
Mm-hmm.
basically a firewall on both sides. And the
Right.
recommendation is often that you use a different brand of firewall, because
Right.
one exploit obviously would work right through the two firewalls. It sort of negates the benefit of them. So they say use
Right.
two different brands.
Mm-hmm.
But yeah, having a physical solution really, is a bit of a paradigm shift in many of those things that you have to do. And like you say, as those are much more managed solutions. So anyway, so I thought that was really interesting.
Yeah, there's actually a parallel to the U.S. government. The solutions we sell to the U.S. government, which are a different product line, they have some of those same. And it's not just recommendations; it's actually requirements that you do different things differently on one side versus the other side. So there's
Right.
a lot of redundancy and uniqueness built into those solutions, as you can imagine. So those are a bit more complex and take a lot more effort to roll out because of what they do and how they get tested and verified. But the crux, the core of that technology is the
Right.
same technology.
That's cool. So we didn't have any more questions come in. So it looks like you did a fantastic job with your presentation. You answered
Okay.
people's questions during it. I'm going to just move forward with what we've got coming up next. If you feel like changing tracks, right now you're in the power track. If you want to go into the water, wastewater, or the oil and gas track, in order to do that, what you're going to do is exit this presentation and then go back into the invite that you received, and you'll see the links there. Obviously, if you exit this one, you want to come back into it, you can just click the link for the power track. Next up, the 3 tracks, is we're going to have Don and Dave from Phoenix Contact talking about advanced pump control, and that's going to be in water wastewater. In the oil and gas track, we'll have Stephen Miller from Endress & Hauser, and he's going to be talking about some new ultrasonic flow meters. And in this track, so in the power track, we've got Jeff McKinnon from JMK Engineering, and Jeff's going to be talking a little bit about central monitoring, utility protection, and control systems. So up now, we've got Jeff McKinnon, who's the president of JMK Engineering, and Jeff's going to be speaking to us a little bit about central monitoring, utility protection, and control systems. So Jeff, you've got yourself on mute there. Do you mind just unmuting your microphone?
Yep.
Perfect. How are you doing today, Jeff?
Pretty good. The sun is shining. It's warm. It's nice.
No, that's fantastic. So Jeff, you're the president of JMK Engineering. Do you want to describe a little bit about, just in a couple sentences, what JMK does?
Yeah, sure. So JMK Engineering is a consulting engineering practice, and we do most of our work in the hydroelectric generation and smart grid and electrical safety space.
Right. Fantastic. Yeah. And I know you have you guys push quite a bit of social media information. I see emails and stuff coming from you all the time. So you're very much sort of in the mindset of working towards sort of public education on best practices and other things.
Yeah, I have a newsletter, which in my presentation, there's a special page for anybody who's on this webinar. So they can go to that page and then find out more about me, find the slides, and when the recording goes live, I'll link to that too.
Perfect. Yeah. So did you want to talk a little bit about what you're going to be presenting today, and then feel free to grab the presentation and go with it.
Yeah. So today, everybody can see my screen now?
Yes.
Awesome. So today we're going to talk a little bit about the distributed protection and control. So we can get going now here. So first, a little bit about me. My name is Jeff McKinnon. I've been an electrical engineer for the last 15 odd years, and I've worked on projects all over North America and South America. If when we're done this presentation, if you go to jmkengineering.com/VTS, there's a special place. That's where you'll learn more about what I do and how you can keep in touch later on. So today I'm going to talk about distributed protection and control systems, and specifically the smart grid and modern smart grid, and how to connect everything together in a safe and predictable way. If you're here for the last presentation, it's actually a decent follow-up. As we go, there's a little question box at the bottom. You can just hit the Q&A and type your question as you think of it. That way, when we get to the back end of the presentation, you don't have to try to remember what was I going to say, and what did I say. So the goals of this presentation, well, I'm going to do a quick introduction of what smart grid is. We're going to talk about interoperability within the utility departments themselves. So a lot of people think about interoperability when it comes to vendors and products. And what I'm trying to introduce is that all the departments within a traditional utility, they kind of operate in silos, kind of the vendors of themselves. And how can we use a interoperability approach, a systems of systems approach, to bridge those silos, those departments, in a predictable manner? And at the very end of it, I'll provide a model framework, kind of an example of how that could work. So let's back up a little bit. So why is this a thing? Why are these departments into silos and they don't talk to each other? So typically, the utility departments are arranged into kind of what you see here. So this is a local utility, and these are all the VP levels. Now, on the day-to-day basis, a lot of these departments are going to be talking to each other, but they're not really inside the departments. They're not working necessarily every day into how does everything work. They're kind of look like black boxes. So you have transmission, distribution, power production. In a utility, those two departments are really producing the power, the revenue for the company. Then we have administrative departments that kind of cover the whole utility. We're going to focus mostly on the technology department or the IT department about how they operate within a utility. So these departments kind of work together. You have a generation flows into a transmission system that flows to a distribution system down to the customer. These departments don't talk to each other very much. So the generation group's not going to talk to the distribution group or the customer metering group very often. The transmission group is going to talk to the generation, a little bit of the distribution, but again, not the metering, and vice versa. So they'll talk to the people who are adjacent to them, but not right across the entire company. One of the groups that does talk to everybody is the IT group. So the IT group bridges essentially all of the departments because they're the holders of the computers, and they take care of the overall business network of the computers. Now, IT in the utility world is very new. Utilities they've been running since before transistors were even thought of. And that's kind of why the structure of the business kind of looks the way it does. Everything had to be within its own little department or its own little box to make everything work in a very predictable manner. When computers were first being introduced within companies, they were managed within those departments. And those computers, they used them to build modern controls for generators. Transmission distribution used them to model their own systems, etc. So it was kind of a ad hoc way of putting it together. Now, when the internet came about, when ARPA came up with a way to connect these networks together, IT was born, and so was smart grid. So this smart grid, the first idea of smart grid in a legal sense was in a U.S. Act in 2007, and the thought was at this time, communication networks were getting cheap enough and fast enough that they could help connect the entire network of power generation and reduce cost. So when you think about that time, right when the internet, everybody's getting computers, the group that had the most authority within the business because it talked to everybody was IT. They became the keepers of the computers, the managers of the networks. So this is kind of where the first friction between operations technology, OT, and information technology started to happen. It's not really a friction, it's kind of made up. They both have very different goals within how to operate everything. But operations technology folks, the people who are operating and engineering the networks for the substations and the generators and then connecting them together with lease lines back to the site, to them it looks the same. But there's some fundamental differences between information technology and operational technology. The life support of the equipment that's being installed, right? There's relays that are still in service today that are older than I am, and they still work fine. So we like really long support life equipment. We being operation, I'm an engineer, consulting engineer. I kind of tend towards the operational technology side of the fence versus the IT side. Information technology is a lot to do with the business of the company versus the operation of the equipment. Information technology is advancing quickly. So you have your computers, you have your software that is changing really quickly versus the minimal changes after commissioning of a industrial network. There's a common platform within IT. The vast majority of IT is TCP/IP based, and it's protocol agnostic. So there's not a whole lot other than TCP/IP. It's all flat, and they use commercial off-the-shelf equipment. So the industry certifications rule, you can think of a Cisco certification for Cisco equipment, Microsoft certifications for the servers, those sorts of things. In the OT world, the equipment is, a lot of it is custom. So it comes with a Allen Bradley PLC or a Schneider PLC or an SEL relay. And then the software is built by vendors like me or internally with the engineering team. So very different ways of thinking about how do you build a system. Finally, time. Time horizons of how fast things happen is critical. Within the power system, especially in a generating station or a substation, the time 16 milliseconds is a lifetime. Lots of things can happen within 16 milliseconds. So you want to keep everything as short as possible. I did a quick ping of Google to see what is the ping time. I have a fiber internet, 1 gigabit, not a whole lot of stuff going on in my network, and it was 19 milliseconds. So that's too long for things to happen within a substation, within a generating station. From my perspective, the idea of quality of service in IT didn't really become a thing until voice over IP started to become important. The idea of routing and giving qualities to certain packets wasn't critical until about 10 years ago. And today, if something happens and it takes 100 milliseconds, that's fine. That's pretty quick. So how are we going to develop a system that has the flexibility to ensure that our control networks are talking fast enough, and that everybody who works on the IT side make sure that the proper authentication, outside access, cyber attacks are taken care of so that we don't have any bad actors operating in our plants? And finally, how do we do this today without building into a huge system, building into a step change? How do we start doing that today with the smallest amount of work? So first off, we just need to make the problem smaller. When I was in school, and then when I started commissioning large systems, I was taught always to break the problem down into very small problems that were really easy to solve. Kind of intuitive, but when I was out in the field first, I didn't think of that. There's two ways I think about this. You have your divide and conquer, where you take your system, you break it in half, see which side's broken still, and keep going down until you figure out where the problem lies. And then second is the first principles. So you take the simplest part of the system, the simplest circuit, prove that out, and keep adding elements in to the system to make it work until you know where all the problems were, and now the entire circuit works. So analogy to this, and this is kind of the analogy to system of systems. You can think of a single circuit with a bunch of elements as a bunch of systems, independent systems. If you're monitoring a sump pump, for example, the circuit itself is designed to turn on a pump or create an alarm if the water level's too high. The circuit doesn't care how that contact is made up. It could be a float switch, it could be a contact off of a level sensor, but it's just a black box. It's just the level is at this height kind of contact. Another analogy is the departments in a utility. So each department has its own thing it has to take care of, its own system, and it has a bunch of systems within that department to make their part work, whether it's produce power, whether it's to produce power or transmit that to the customers. So we have to define those systems. So this is a figure out of from NIST, National Institute of Standards and Technology, and the conceptual domains for a smart grid network. So the different groups of people that are heavily involved. So we have our generation group, transmission, distribution, customer, and operations. We're going to focus a lot on generation, transmission, distribution, and then the operations up here. So first, now let's think of timescales too. First, the system operator here wants to know on an instantaneous basis how much energy is the customer need and how much energy are we producing, and then how are we going to get it from point A to point B. That needs to be done relatively instantaneous. They want to know what the current power requirement is, plus the reserve, and then what's it going to look like in the next 5 and 15 minutes. And then next, we'll look at larger time horizons. So the next hour, the next shift, etc. Finally, the engineering group or the asset management group or the planning group are going to be wanting to look at farther out horizons, planned maintenance, future capacity. For the sake of hydro, what do the reservoir levels look like? Those are long-term horizons that don't have to happen in a synchronous manner. So it doesn't have to take, it can take an hour, it could take a day, but it doesn't have to be instantaneous. They still need to be. So an example of some asynchronous status feedback would be the case of a protection relay trip. So within a substation itself, you can have protection that will communicate to a breaker, essentially, with a hardwired connection. That's going to trip that breaker based on a current feedback, voltage, etc. Or you could have a transfer trip scheme from a substation to a generating station, or vice versa. That control action can be outside the normal IT network, stay inside the OT network, and those statuses be communicated back to the system operators, so they can make the necessary changes to their operation but that can happen relatively slowly, maybe in the time of seconds if it's a automated action, versus the microseconds or milliseconds that the control actions happened. So I think I have a plan. I have a plan of tying all this stuff together. You know, it's relatively agnostic, but we want to think about it as interoperability of all the systems tied together. We're going to break the big system into a bunch of little systems that are easy to talk about, easy to work with. We're going to add predictability to the IT group, all the engineering groups that are interested in the information, and the operations of the people who are operating the plants. And we're going to keep the expertise and the engineering controls within the domains that the experts lie in. So we're not going to expose these plants to the outside networks we're going to expose them in a fashion where the IT group, who has the expertise in cybersecurity and functionality in those domains, are the ones who own that portion. And we're going to do it in such a way that we don't have to install a whole bunch of new equipment and spin up a whole great big engineering project. We can start this small and have it flexible. It's a big claim. Well, we'll see how I do. So what are the smallest parts of a system? So here's a sketch I did for a client of mine at one point of what is a smart grid. So we have our utility IT there right in the middle with all these little dotted lines going out to the different areas of the networks. So my thought is the types of areas that are going to be the most obvious nodes of communication are going to be your generating stations, your transmission substation, your distribution substations. We'll leave the customers alone, because once you add smart meters and things like that, you open up a brand new set of challenges, and that's kind of the scope of the next 20 minutes that I have here. Generating stations typically interface with the transmission system, and then you have a step-up transformer. Now, that's the demarcation point, right? But for utility, it could be on either side of that transformer, not important. Transmission substations, that's where all the bulk power is switched, stepped up, moved around, and then down to the distribution substations that take it to the last mile. So the way that I'm thinking about this is your network here, starting at the generating station, takes care of all the data that takes to make that power up to the communication point of that node. And your transmission substation takes care of all the data that's within the fence of that substation, going down to the next distribution substation. Distribution substation takes care of all the data from there to the last mile. This would include all of the information that's needed to operate the individual assets or individual nodes independently from the rest of the system. So if something blew up and all of your IT network is gone away, you can put some wet computers at each one of these sites to operate the plants. So the operator would be sitting at a terminal in the generating station, and they'll know all of the levels of the reservoir and how much power and frequency and voltage, and be able to produce power onto the transmission system. Locally at the transmission substation, there'll be a terminal station that has all of the information that they need to know how to operate that part of the system, and so on. Hydro station is a nice, simple example because all the information that they need is mostly to do with watershed, some management control of that watershed, so how much water is passing through, generator protection, generator control, some instrumentation of the plant, and plant control. Unlike coal and gas plants, which are massive systems. So most of my examples are going to be in the hydro space. Protection relays would manage all of the protection equipment of the system, personnel, any arc flash relays that you might have, and then report those statuses back to the operating station. And then generating controls will do the same thing. Now, the location of this equipment doesn't matter for this analogy. It can be individual pieces of hardware, so protection relays, an AVR, a governor, a balance of plant controller, etc. Or it could be routines on a single controller. The idea is that if it's a routine, the protection engineer is the one taking care of the protection routine. The governor, for the governor control, it is the electrical and mechanical engineers working on the governor controls. At a substation, it would be something similar. The local operator will have control over everything within the fence of that substation and all components that are downstream towards the customer. This might include reclosers, capacitor banks, etc. And then all that data is brought back to the local operating control station and integrated with the local HMI. So now that we have the OT figured out, how do we connect that to the enterprise? How do we connect that to the overall arching utility, the business? Well, this is where we're going to include a new piece of equipment. It could be a traditional RTU, a remote terminal unit, but typically those are operating on DSL links, leased line, or microwave networks. They don't necessarily have the bandwidth to handle the amount of data that we want to be transmitting in the modern era in 2020. So what I recommend to do is use the existing communication network. So our TCP/IP Bell TELUS network. And piece of equipment that I prefer to use for the RTU is something like a SEL RTAC. And I'll get into specifically why the RTAC is attractive to me later on in the presentation when we give a couple of examples of how you would set this up. So the RTAC is a piece of equipment that would connect just before the firewall. And it would connect to all the station controllers, the protection relays, etc. And how they connect, they could be connected in parallel to the station controller or get that data from the station controller. And time is the important factor there, is how fast does that data need to be updated in the enterprise network. And then finally, it's connected to that IT firewall, or if you were watching the presentation earlier, a data diode that then will make sure that the IT group is responsible for. They'll make sure that all of that firewall, all the data is secure and that connection is secure back to the enterprise servers. Finally, that's a single point of connection. So you have one connection point between the IT world and the OT, the enterprise, and the industrial facility. and it's a single cable. So when they're troubleshooting on site, it can be an asynchronous troubleshoot. It works on this end, it works on this end. All right, so IT. First off, standardize everything. So IT has the disadvantage of having to work with the entire company. And in the generation world, if you're only dealing with generators and breakers and watershed stuff, you can build a really complex tag naming structure that works for you. T&D, they can do the same thing. Anybody customer facing, they can do the same thing. But when you try to put everything together, it doesn't really scale well. So what I suggest to an IT group is come up with a recipe that makes it easy for you to, for the engineers and for you to teach other groups how to come up with the data that they need. Next, come up with a process and a standardized table that looks exactly the same for every asset type, whether it's a generator or substation, breaker. Break it up however you want and however makes most sense. This way, it'll allow you to come up with a system that will scale depending on the size of your assets and what types of assets are in the site. This is those 4 hours that you're going to spend sharpening your axe before you start cutting down the tree. All right, so now I'll get into a couple of the structures that you can use. My preference in general is, and because I'm a consulting engineer, I'm not representing any product, I can give you my suggestions. So I use SCADA, VT SCADA for most of my historian and SCADA HMI applications. And I use SEL for my RTAC and protection, for relays almost exclusively. So in this example, we're assuming we have really good connectivity wherever the stations are, wherever the generation plants are, and it doesn't go down very often. Or if it does go down, the data that you're going to lose is not that critical. Because the IT group's gone through and decided what the various groups and entities need within the organization, they can create all of their widgets that they need to be built and create their standard tables in their VT SCADA application. That means every substation, every generator will have similar I/O, similar points, but some of them might be blank. This reduces the amount of development time per site drastically. It takes a lot of time to get it done the first time, but after that, you're done. When you have, for Nova Scotia, for example, there's 34 generating stations for small hydro. So if you take a little bit of time to do the first one, you can do the rest of them really quickly. So with this scheme, what we have here is a RTAC that's gathering all the data, going to a firewall. I'm saying a VPN tunnel, or whatever the IT world thinks is important, to another firewall. Something that Dave mentioned earlier is making sure that these firewalls are different manufacturers is helpful in ensuring that you have high security. Similar, when you have multiple relays for a critical substation, you'll have a primary and backup. You want to have those as different manufacturers too. It's all tied to RTAC. Now, if you use an RTAC 3530, it has a little HMI built right into it. So in this application, your VT SCADA server, which is grabbing all of this data in real time, well, the operator, you don't need another VT SCADA license for the substation. You could buy a thin client license, but this RTAC comes with a free HMI. So it's not really necessary. Now, in this next example, we're assuming that there's weak communication infrastructure. I'm going to be using, for most of my terminology, VT SCADA 11 versus VT SCADA 12. I haven't done a lot of applications in VT SCADA 12, so I'm not exactly sure how this would change, but I'm sure Dave would be able to help you out later on. So the way this is set up in a similar way that I've done for a previous client who owns small generation assets throughout Atlantic Canada. Now, one of their assets is a small plant in remote Labrador, and they have poor communication. So what we wanted to do is make sure that there was a way that we don't lose any information over time, but that the client still has a single place that they can log on and view all of the other sites. So what we've done is we have a master application in their headquarters and VT SCADA servers, sometimes two, in there with all their assets. And we use area level filtering to make that happen. If you're working with a larger utility, you can do the exact same thing. They can have area levels filtering for all of their generation stations, for example, with one master application at the data center. One of the advantages of this hierarchy is that now at all of their generation stations where they have a lot of moving parts, for example, they have a full-blown HMI SCADA server right there on site that allows them to back everything up. And if there's ever a breakdown in communication in the between these two firewalls, all that data stays backed up. And finally, the operators can use that SCADA server just like they'd use any other SCADA server and have operator network notebooks and historians and logging, etc. So finally, now what if we had an example at a substation like this, but we didn't have any communication relays, or we had old reclosers, but we still want to get some of the statuses back so that the VT SCADA, the operations, and the engineering managers are able to get this data. Well, then we can add a simple firewall, an RTAC 3530 that has 24 DIs. And again, we can still use that integrated IO, HMI manager, to monitor all those assets. That means that if we have old relays, it's not going to stop us. We can just hardwire those in. It keeps the cost down so that all you really need to buy when the time comes is an RTAC and a firewall, and then set up your VPN tunnel, and you're done. All right, so that pretty much covers it. This presentation was it was a lot of information in a short period of time. I wasn't trying to pitch any one way of handling this challenge. I just wanted to make sure that there's an idea out there of how to start this conversation. I'd like to thank Trihedral and for having me, and Dave for sending along that invitation. Remember, if you go to that website, you'll have more information. Some things that we didn't cover. This is just the start of this conversation. How does a utility use existing infrastructure and the legacy organizational structure to build a smarter grid without adding risks to the company? We talked about some background of how utilities in general are structured and what we can learn from their history of why they're structured that way. And finally, some continued discussion. So a lot of this presentation was based on the plug-and-play electricity era, interoperability to integrate anything, anywhere, anytime. It was in the PE magazine in the fall. And then if you want to know more about Smart Grid, IEEE Smart Grid is a free and open community for Smart Grid professionals. A general member, you get free access. It's free community, not just free as in open, but free as in beer. And it has a monthly newsletter and live webinars. And if you happen to be an IEEE member and you join the community, you get free access to the resource center. And then finally, NIST has a very good website for Smart Grid in general. So that's how you can contact me. If you have any questions, use that Q&A box, and I think Dave will let me know if there's any questions.
Perfect. Yeah, I've just looking at the question window here. There isn't any questions in here yet. We'll give people a chance right now to type in any that they may have had, and we'll go with that. So in the meantime, Jeff, thanks very much for your presentation. I thought that was really interesting. I really liked your breakdown as well of the different ways to solve problems. I always have been a big fan of the old NASA quote, and it's not the most popular one. It's one that's actually often used out of context. It's used in the context of Apollo 13 when actually I don't think it was ever said during an Apollo 13 mission. But one of my favorites is the idea: keep working the problem. You know, you see a problem, and part of keeping to work the problem is obviously understanding the different ways to break the problem down. So you're not just staring at a concrete wall and, you know, trying to wonder how you can get through it.
Yeah. So, making everything simpler is always easier.
Absolutely. Yeah. So that was fantastic. So I still don't see any questions coming in. So I'm going to congratulate you on an excellent job for answering everybody's questions during your presentation.
Yeah, that's always a good feeling.
So next up, I'll just note before we go into it is that there's 3 concurrent streams going on right now. There's a water wastewater stream, an oil and gas stream, and a power stream. Right now, you're watching the power stream. And coming up in each of the streams is in the water wastewater, we've got Travis Smith from Census. He'll be speaking a little bit about the water utility of the future. In the oil and gas stream, we've got Mervyn Betts of BetSum Controls, and he's going to be talking about distributed SCADA. And in this stream coming up is Gautam Ashikumar and Jeremy Blair, and they're going to be talking about economical arc flash mitigation. Next up, we've got Gautam Ashikumar and Jeremy Blair, both from Schweitzer Engineering Laboratories, and they'll be speaking about economical arc flash mitigation. I see, Gautam, you've got your computer on. Did you want to introduce yourself briefly there?
So yeah, thanks for this opportunity, Dave, and so looking forward to this presentation. So I'm Gautam Ashok Kumar, and I'm an application engineer based out of the Alpharetta office in SEL. And I've been working as an application engineer for a little over 2.5 years now with SEL. And currently, I support the region of North Alabama for protection and parts of Tennessee as well.
Right. Okay. Very cool. Thank you. So, and Jeremy, I see it looks like you just come in there. I had you accidentally blocked. So sorry about that. Perfect. So, and did you want to introduce yourself quickly, Jeremy?
Yes, certainly. Thanks again for having us here. My name is Jeremy Blair, application engineer with SEL, just like Gautam. I'm in our Jackson, Mississippi office. Been with the company about 6 years or so. And been a great place to work, and we're excited about these kind of applications, and excited to share this with you guys.
Very cool. So for those who are just joining us, this is the Automation Village. Next up, we've got our last session of the day, and that's Schweitzer Engineering Laboratories talking about economical arc flash mitigation. And this session's going to be about 40 minutes long, and then we'll go into some questions. If you do have questions, you will see a Q&A box down in the bottom of your console there. Just post your questions there. We're monitoring the Q&A box, and then toward the end of the presentation, we'll jump in, we'll go through the questions and do the answers to those. And also the session today is being recorded. So if you didn't get to see the session that you wanted to see, or you want to review something from a session, then just look for those recordings and you'll be able to go back through and cover everything again. All right, if you guys want, feel free to take it away.
Okay, yep. Thanks, Dave. I'm going to start sharing my screen now. So can you see my main screen, the presentation screen?
Yep, able to see it. It looks great.
Okay. All right. So I'm going to go ahead and get started with the presentation. And so the topic of today's presentation is economical arc flash mitigation. So I'm going to be presenting along with Jeremy Blair, and I'm going to, in my section, start by going over the physical phenomenon of arc flash and how and why it occurs and the damage it can cause. And then I'll also touch upon the standards that address arc flash hazards and protection. And then we look at it from an engineering perspective as to what factors go into deciding the amount of arc flash incident energy that can occur. And then I'll hand it over to Jeremy, who will explain what we can do to mitigate the effects of that arc flash, and then talk a little more on those lines. So we've all heard of arc flash. We know it's a dangerous condition that can cause enormous damage to both equipment and people. And so the energy that's caused by that, the formation of that arc, is proportional to the electrical energy that's available, which in turn is the product of the voltage times the current times the duration that this arc persists. So how does that arc flash incident first occur? So if you could have a short circuit between two phase conductors, or a conductor from phase to ground, especially when they're in close proximity to each other, like in a switchgear cubicle or so on. You can have an excess amount of current flowing through that short circuit, and because they're in close proximity, cause the air around it to ionize, and ionize so fast that it can break down that air insulation, and the current literally arcs across the air, and with it, it's accompanied by a big flash of light, like you see in that photo taken probably with the video captured at a few milliseconds after that arc occurs. And so that rapid ionization causes so much of heat that it can expand metal, blow out shrapnel, and cause all sorts of damage. In fact, an arc flash is pretty much the hottest temperatures that you'll see on Earth, with temperatures exceeding or going up to 35,000 Fahrenheit. And just in relative terms, electric arc furnaces used in steel making can have temperatures that touch 5,000 Fahrenheit in comparison. So talking about arc flash, and then the blast that occurs with it because of the expansion of air, called the arc blast, is also a phenomenon that accompanies that arc flash. And then there's another term called the arc flash incident energy, which is the energy at that working distance, and you typically measure that in calories per centimeter square, or in joules, or in equivalent joules per centimeter square. So looking at the units, you can see that the closer you are to the source of this arc flash, then the energy that's incident on that surface increases quadratically. So as we talk about distance and understand its effect on the arc flash incident energy, there are standards such as the NFPA, the National Fire Protection Association standards, particularly the NFPA 70E, that defines certain boundaries and categorizes the hazards associated within each boundary. So first, if we sort of look at that location of that energized conductor, we define a working distance from it, the working distance that between this arc point to your head and body, and so on. And then we see that we have an arc flash boundary, and the arc flash boundary is a calculated boundary. So it's the boundary, or the distance within, or distance from the live conductors within which an arc flash incident can cause a second degree burn. And a second degree burn in terms of the arc flash incident energy is 1.2 calories per centimeter square. And then we have the limited approach boundary, which is a distance within which you have a shock hazard. A shock hazard exists within this boundary, and only qualified personnel are allowed to enter this boundary. And closer from that, closer to the energized conductor is the restricted approach boundary, where you define that boundary based on the increased likelihood of an electric shock. So all this is important, and if we just look on the internet or just within the industry, you'll read and hear a lot about arc flash in and in literature and so on, because of how dangerous and commonplace it is than we think, right? And OSHA reports that there are at least 5 to 10 reportable incidents in just the US alone every single day, with at least 1 fatality every day. So it's important to do everything we can to reduce those hazards. And in the next slide, you can see a picture of an arc flash incident scene. And this arrangement is all post that incident. You can see there's a lighting arrangement and so on. This was all done post that incident. So apparently there was the incident was caused by an unsecured cover on a mounting plate, and this is the 480 volt cubicle, and they also had the substation secondaries tied together, which also caused an increased amount of available energy. And the estimates suggested that the energy was beyond 60 calories per centimeter squared. And just recalling what I mentioned earlier, a second degree burn is caused by 1.2 calories per centimeter square. So taking a closer look at the damage to that cubicle, you can see it's completely charred around in the inside, and you can see these burn marks on the top of this cover plate provision right there. And based on the records, it was found that first the rightmost phase came in contact with the ground and quickly escalated to 2 phases and then became a 3-phase arc. And it's not uncommon for an arc flash incident to start off as with a single conductor exposed to another conductor, and then immediately evolving into 2 conductors and then 3 conductors and so on, because of what I mentioned earlier. It just weakens the air around it, and then suddenly the air becomes a conducting path and creates an arc around it, and just quickly things escalate and cause this damage. And here you can see more severe damage from an arc flash incident taken from a mine. So this switchgear was part of a mine, and you can see that it caused all sorts of damage, from burns to melted metal and shrapnel and everything that you can possibly imagine. So this is just the effect on equipment alone. And if we start talking about the effects on personnel that are involved, with these equipment, then you can see that there are damages caused through infrared and infrared and UV radiation that can cause eye damage. The arc flash is accompanied by that blast, and that blast is powerful enough to knock people off their ladder or just knock them off the ground. And with it comes a lot of melted metal, shrapnel, and fatality that can occur mostly because of burn injuries. And you also need to touch upon the fact that post this incident, if you do have technicians or workers survive this incident, they can also have psychological issues. And reports talk about how workers show apprehension at the workplace post experiencing an incident like this, which is pretty understandable considering the effects that they experience. And so what are the standards governing arc flash, and how do we evaluate this risk? So talking about arc flash, there are mostly 3 major standards that talk about this. To start with the NFPA 70E, the National Fire Protection Association standards. So they provide specific guidelines on safety, including how to mitigate the arc flash hazards, and also provide guidelines for selecting personal protective equipment. The IEEE standard, on the other hand, the 1584-2018, provides more of a rigorous approach and calculations on how to get that value of incident energy that occurs with the arc flash. And then you have the NESC, especially the NESC C2, which provides some guidelines when you're trying to evaluate arc flash on other systems like a distribution or transmission system, where you may do a single phase arc flash evaluation, or do an arc flash evaluation for a system, let's say beyond 15 kV, which it's not within the scope of the 1584 standard. And so here's an example of a table from the NFPA standard, which lists out the minimum PP requirements for each hazard or risk category that you evaluate the equipment to be at. So taking a look at this, you see that if the risk category is lower at, for example, a category 1, then you have a basic FR shirt and FR coverall, and then that's one layer. And then as the risk category increases, you see, for example, in a risk category of 3, you see the number of layers that come in. You start wearing the FR shirt plus an FR coverall, which in the industry you may have heard of the term bunny suit. And then you go into category 4, you also have to wear an extra layer with a multi-layer flash suit, or in the industry you commonly know it as a moon suit, right? So you can see that just having a higher risk category or having a higher incident energy means you'll have to equip yourself for that amount of you'll have to equip yourself with that amount of safety clothing. So with all that said, in terms of avoiding, in terms of the hazard, the best way to avoid the hazard is to eliminate that possibility, right? I mean, it sounds pretty obvious when someone says, try to de-energize the equipment if you can, but it's a good idea to, to think about it and reevaluate this option and see if you can eliminate that hazard by maybe, considering if that can be de-energized at some other time, and if that job can be done at a different time, and so on. NFPA's hierarchy of risk controls, for example, mentions eliminating the hazard as the first line of defense, and then you have other forms of control like engineering controls and various other methods. And PPE is literally the last line of defense, right? And it makes sense, because if you think about wearing, let's say, a moon suit and performing these operations, then you may also have that limited amount of maneuverability, and end up exposing yourself to that equipment for longer than you would if you had a lower risk of exposure and had to wear lesser number of layers for that particular hazard. And so restating that, first option, as much as possible work on de-energized equipment, and understandably it's not possible at all cases. We need to have, sometimes the equipment needs to be energized. In that case, we need to evaluate options to be able to rack the breakers remotely and use communication accessories whenever we can to perform operations such as retrieving data or sending in data and so on. A lot of times, even without human intervention, arc flash events can take place. It's not always that a mistake or using the wrong tool causes an arc flash. So we need to be aware that as much as we can, we need to minimize the exposure, and we need to minimize the amount of time we're around that energized equipment, right? And so if you think about it, taking communications one step further, a lot of these processes can be automated, because event retrieval, metering. These may be some things that you want to do on a regular basis, and these can be scheduled with automation devices such as an RTAC and software that go along with it to collect this data, and then collect this at a regular interval, and then not have that human layer attached with this operation. So now that we understand the hazards and how to avoid them, so how do we exactly measure how much of that arc flash incident energy can be expected, right? So to do that, NFPA and IEEE 1584 both provide those guidelines, but we need to collect a lot of data to be able to calculate that exact amount of energy. So as far as the system data and operating modes are concerned, you remember I mentioned that in that first example that two substation sources were tied together, contributing to a higher incident energy. So those type of things need to be taken into account, right? You need to know at what mode you'd be operating at for the worst case, and what the transformer impedance is, whether you'll have additional feeders that need to be on, what generators may be in service, and so on. And calculating the bolted fault current and the arc fault current is also necessary. So you see that the arc fault current may not be the same as the bolted fault current, because a bolted fault is through a bolted conductor, whereas the arc fault arcs across the air. So it comes with a little bit of impedance. So while the arc fault current could be lower in impedance, that doesn't necessarily mean that that fault current is going to cause lesser damage. So thinking about energy, energy is really, the voltage, current, and time. So having a lower arcing current may introduce a higher amount of fault clearing time, depending on, again, how your relay is set and whether you have those inverse time characteristics and so on. So just something to think about. Just having lower current doesn't equate to lower energy. System voltage, equipment classes, and distances. So all these things come into play when it comes to calculating arc flash energies. And the 1584 NFPA guide provides some common working distances, and something that you can base it off of that as well. And all these put together will give you the incident energy and also the arc flash boundary that you can estimate. Here is an example of an NFPA 70 equation that provides a method to determine the arc flash incident energy at a piece of equipment. So if you kind of look at the equation, you can see a lot of numbers are involved, but just highlighting those factors that are involved, you can see the distance, inversely proportional to the distance, directly proportional to the time, and then also depends on the fault current right there. So just blurring out the other aspects and then focusing on this aspect, we see that it's the fault, the amount of energy is proportional to the time that energy is available, right? And so going to the IEEE 1584, which provides a more rigorous approach to arc flash incident energy calculations. You'll also see a number of other factors are involved, but then again, focusing on just the aspects that are highlighted, you can see again it depends on it uses the arcing fault current as opposed to the bolted fault current, and again directly depends on how quickly you can clear that fault, right? And this is a factor that we can control with maybe equipment that we have, or maybe with very little additional equipment to drastically reduce that amount of energy. And so with that, I'm going to hand it over to, or let Jeremy take over the screen and continue from here.
Yes, thank you, Gotham. And hopefully you guys can all hear me and see my screen, my overcurrent relaying slide, if I can get someone to just confirm that for me real quickly.
Yeah, I can see a slide here.
Excellent, thank you, Gotham. So, you can see from the slides Gotham shared with you guys, arc flash is it's certainly a very real risk, significant risk. You see from the pictures, it looks like a bomb went off in that switchgear, and that's really the way people describe an arc flash incident. It's like a bomb goes off, and the same risks to personnel if a bomb were to go off is really what our technicians and our engineers face in an industrial environment around this much energy. Those switch gears are routing an incredible amount of energy every moment of every day. And sometimes it's easy to forget when we're standing next to it, thinking we're safe just on the other side of that steel. But we can see from these from the pictures Gotham shared, it's the damage of an arc flash incident. There's no amount of simple steel that can really protect us from it. So we have to take all these other measures. We have to be able to assess the risk. You can see from those equations that assessing the risk, coming up with the amount of arc flash incident energy that could be present, is a complicated task itself. But like Gotham showed you, no matter how complex any of those equations get, time turns out to be the easiest lever we can pull to adjust the available arc flash incident energy. And that's great for us because no matter who you are, where you are, what your installations look like, you've got some sort of protective relaying there. We're going to talk about some SEL solutions, but honestly, some of these solutions can even be employed using anyone's, just about anyone's relaying. So I'm not sure if everyone's familiar with typical protection here or not, but if you are, then you'll recognize this diagram here. Pretty typically might have a source here feeding my transformer. Secondary of the transformer comes into my switch gear through a main breaker or an incomer, depending on terminology you like to use. And then coming off of that, the bus inside the switch gear will have several cubicles for feeders. And if there's a fault, and not necessarily an arcing fault, but any fault on my power system, I'm relying on relays here that are measuring the current on the power system to identify the fault and command a breaker to trip, and hopefully the right breaker. So that introduces us to a term we use in protection called selectivity. So if this fault here occurs, the one here on the feeder A, we want the feeder breaker A to trip. We don't want the main breaker or the incomer B to trip. However, the fault current flows from the source to the fault. Both relays will see the fault. Both of them will begin to take action. So classically, we use time as a means of establishing selectivity. We can coordinate protection between the two systems using something like a time current curve, where you can see here, the higher the current, the lower the time response of the relay. Lower current gives a higher time response. And so for any available amount of fault current, I would expect to see relay A timeout trip before relay B does. And this gives me the selectivity I need. It means that when there's a fault on the feeder, that I won't trip the bus. I'll only trip the feeder and leave all other feeders off the bus in service. However, it also means that when a fault is on the bus, I've got to wait around all this time before I trip. This is what leads to high clearing times, which in turn, back to some of these equations here that Gotham shared with you, the higher the time, the higher the arc flash incident energy. So if I want to reduce arc flash incident energy, what I want to do is speed up my protection times. So how can we use the protective relaying that's already there to do this? There's a lot of schemes we can employ. In fact, there's even some schemes that aren't shared here. This particular presentation is focused on using what would typically already be present in a lot of switchgear schemes, which may just be protected with overcurrent relaying, like we showed there. So there's a fast bus trip scheme, or you may have heard this called a zone selective interlocking scheme, that we'll talk about. We can also talk about the use of just simple instantaneous overcurrent relaying. There's some trade-offs to that, but we'll see the benefits and the shortcomings. Then finally, we're going to talk about a light and current-based arc flash detection method that we're very proud of. It's really going to be the fastest method of clearing an arc fault that we've seen yet. So fast bus trip scheme. I mentioned the term selectivity, and we're going to use time as a means of establishing selectivity. But what if I could use something else? What if instead of time, I could use communications? If each of these feeder relays had a way to tell the main relay that it saw a fault downstream, then the main relay wouldn't have to rely solely on time to know when it should trip and when it shouldn't. And so with a scheme like this, we're showing a logic processor or some sort of communication processor between each of these relays. Let's say, using a 50 or an instantaneous overcurrent element to say, yes, there's a fault downstream. Let me tell the main relay about it. This can even be employed with simple output contacts wired to an input contact on the main. So it doesn't even have to employ digital communications per se. But if I can do that, then now my main will still have its typical time over current characteristic, and my feeder will still have a time current characteristic that's faster than it. But if I employ an instantaneous overcurrent element on my main as well, then I can hold that element there, let it pick up, give myself a very short time delay right here, just to make sure I don't get a blocking signal. And if this guy sees a fault, but none of these feeders send him a blocking signal, then we know the fault must be on the bus. If the fault is on the bus, I need not wait all this time. I can trip after this short time delay. So this is great because this gives me a relay response time on the order of about 50 milliseconds or so. Of course, the duration of the fault would be this plus the breaker clearing time. But if you consider that without this, we may commonly be looking at anything from 100 milliseconds to 500 milliseconds in a typical timeout on this timed main overcurrent curve. 48 milliseconds compared to 500 milliseconds is a significant reduction, right? We've cut the arc flash incident energy almost to 10% with that one step alone. Really, the only downside to it is there's a touch more complexity, given not much more complexity. So this is a really popular option. We have a lot of SEL customers that do this in order to lower their arc flash incident energy. We probably have just as many, if not more, that employ a simpler solution, is actually faster as well, but it's less selective. But we can enable an instantaneous trip on the main or on any piece of any relaying for the apparatus that we're performing maintenance on. We can enable that instantaneous trip just while I'm performing that maintenance on energized conductors. In utility spaces, this is commonly called hotline tag, right? So some of our relays will have a button dedicated for this purpose on them. In a lot of industrial spaces, I hear this referred to as maintenance mode. But either way, we can use push buttons, programmable push buttons on the relays or inputs on the relays, and bring that that push button or optical input into the programmable logic offered in SEL relays to provide supervision. So we can turn on a latch, and when that latch is on, that would allow an instantaneous overcurrent element to trip. When the latch is off, it would block it. So I can walk up here, I'm ready to perform my maintenance. I'll walk up to the relay, press this button. With cell logic in the relay, I can have the relay turn this light on next hotline tag to indicate that the maintenance mode is turned on or the hotline tag mode is on, and that if there is any overcurrent condition, that the relay will trip instantaneously. That does, of course, mean that if we go back to this diagram, it means we're going to lose selectivity. It means while maintenance mode is enabled, if there's a fault here, then I'll overtrip. I won't trip selectively, but that's a risk that we're typically willing to take when we know that a person is working on that energized conductor or in that switch gear, and that should there be a fault, we would prefer to just clear it immediately and limit their exposure to a potential arc flash incident. The advantage here over the previous scheme is I don't have to wait for a blocking signal. I do lose some selectivity, but I don't have to wait for a blocking signal. And so I can trip even a little bit faster in about half the time. So now we're looking 24, 25 milliseconds, basically a cycle and a half. So it's basically just the filter delay time typical of digital relay. Of course, some downsides yes, there's the loss of selectivity or loss of coordination, but also the fact that I've got to manually turn it on and manually turn it off. So there are some human performance errors that are still possible there, right? We may forget to turn it on, which would be a devastating human performance error, but we could also forget to turn it off, which could lead to nuisance tripping once I start putting the gear back in service, start trying to start motors, that sort of thing. So how do we take what's good enough, have some compromises, and make it better? How do we make an arc flash detection scheme that is secure, reliable, fast, and easy to use? So I'm going to introduce you guys to our light and current-based arc flash detection method, in which we will certainly still measure current from the system to determine that a fault exists, but we can determine selectively by placement of a sensor, and we can determine that it is an arc fault specifically by what we're measuring with the sensor. So we employ an arc flash light sensor, literally just an optical lens that receives the flash of light, brings it to a receiver inside the relay, and now the relay has the ability to know that there's been a flash of light in a specific zone of the switchgear, and that there is current bigger than normal that suggests there's a fault. If I know there's a fault, and if I know there's an arc, what should I do? I should trip, because that fault is not somewhere else. That fault is in my switchgear. It's an arcing fault in my switchgear. I need to trip, and I need to trip quickly. So that does away with the requirement to use time for selectivity. The other thing it does, the light builds up very fast, and because this overcurrent detection doesn't have to have a very tight reach, it just needs to know that there's a fault or there's not one. It's just a simple fault detector. That means we can use very, very fast filtering on the light detection and on the current detection. And we can combine the two to secure it so that we make sure we're not false tripping for, say, somebody inspecting the switchgear with a flashlight, or false tripping on, say, a motor start. So we use the combination of light and current together to declare that there is a fault, and it's an arc fault, and we need to take our fastest response time we can. So how fast can we go with this? Here's an example of an arc flash event. We can see that while the event lasts for a little while, the light starts building up immediately, and the current starts to increase immediately. When we set selective coordinated protection, we need a good cycle and a half to get an accurate measurement of that current and to set very specific reaches. But when we just need to know that there's a fault here and there's some light here, we don't need nearly as much information. We can get by with 1 to 2 milliseconds worth of information, and that leads to trip times that are on the order of 2 to 5 milliseconds. So we've gone from a relay taking maybe 100 to 500 milliseconds to time out on a 51 inverse time overcurrent curve, down to almost instantaneous at 50 milliseconds, down to an instantaneous filtered overcurrent element at 24 milliseconds, now down to beating the filters in the relay even, and calling for a trip in as little as 2 to 5 milliseconds, coupling that with our high-speed contacts on the relays, which have a operating time of about 50 microseconds. We are now looking at an arc flash incident energy that's dependent pretty much just on breaker operating time. And so we've gotten about as fast as one possibly can get with the existing breaker technology we have today. Because it's completely selective, you can leave it on all the time. So that does away with human performance errors. Because it's selective, we don't overtrip even when personnel are present, but also because it's selective and I can leave it on all the time. If you remember some of those pictures Gotham showed you at the beginning, there wasn't any information about what happened to the people that were involved in theirs. There may not have even been people involved in those faults, but we can see that the switchgear was damaged catastrophically. So even if we take the practices to limit our personnel exposure to switchgear, we still would rather not destroy our switchgear when an arcing fault occurs. And you'll see some of the benefits play out there in some of the case studies we have at the end. So again, kind of reiterating the reduction we can see, that this would be an example where maybe we start off with an incident energy of 120 joules per centimeter squared, or if you're more familiar with the calories per centimeter squared, it's basically going to be 1/4 of this. So 120 joules per centimeter squared would be roughly 30 calories per centimeter squared. And if you remember the categories Gautam showed you at the beginning, you can see as we step down through each of these possibilities, we're able to step into more comfortable PPE protection zones. Right here at the fast bus trip alone, we get down to about 6 calories per centimeter squared, which means I'm in category 2 PPE. And if we employ the light-based arc flash detection method, this can actually get us down to about 4 calories per centimeter squared. So you can see, even though fast bus trip or an instantaneous trip, these solutions help us reduce the arc flash incident energy. Going even just a little bit further with the light and current-based arc flash detection method could even be the difference in getting down to one more category, to the next lowest category for your PPE. Physically, what does this look like? Well, I told you guys we have some light-based or some light sensors. We have 2 forms of this. We have a bare fiber sensor. So this is basically you can think of this like a distributed lens. So this might run the length of your bus compartment in your switchgear. It could also be run from cubicle to cubicle to cubicle to cover multiple feeder cubicles. But this is something that would need to run in all the compartments where an arc flash could occur. And you can see that because it's clear, it will capture the light, and that light will travel down the jacketed portion of the fiber to the connector here, where this will connect to the receiver on a relay. We also offer a point sensor, which is just a single point lens. This can be used to give us a little bit better selectivity if we wanted to. This would allow us to put point sensors in each cubicle that feed back to a specific channel on the relay, so that we know based on which channel picked up the light, we can know which cubicle the flash occurred in. As for the relays that receive these sensors, if you're familiar with SEL products, or even if you're not, this is what they look like. But if you are familiar with SEL products, you've probably seen 751A and 751 relays before in feeder and in main positions. You may have seen the 710-5 motor relay applied. And these relays, on the back of them, they've got a card that will receive those bare fiber and point sensor loops, these connectors right here, the V-pin connector. We also have the SEL 849 motor relay, which is designed more so for application in a low voltage bucket or in a motor control cabinet. And you can see it's actually got an arc flash detection lens built onto it. And we'll talk about how that gets applied. This is almost more of an arc flash sensor, although it can do arc flash protection on its own as well. So what the whole system looks like together, if this is my piece of switchgear, I've got a main relay here on my incomer, and I might run the bare fiber loop the length of the bus compartment, like I mentioned earlier. On independent channels, I might put a point sensor into each feeder cubicle so I know which cubicle it came from. And if I see an overcurrent condition here through these bus CTs, and if I see a flash of light on any one of the sensors connected to this relay, you can see based on where I've put them and where I've covered, we know that if any of these receive a flash of light, that those are in the zone of protection of the main breaker. And so we would couple that current and this light to determine that we should trip this breaker as quickly as possible. Same time, I would love to employ the same technology on my feeders as well. Granted, if there's a fault in my feeder cubicle right here, I need to trip the main, and I have the point sensor going back to the main relay to let me do that. But if I put a point sensor on my feeder relay looking at the cable exit, and I'm able to determine that this flash occurred downstream of the feeder breaker, then I can isolate this arc fault by tripping the feeder breaker. Now I've improved selectivity even further by allowing myself to leave a bus in service even when I'm responding to an arc fault. And then I can perform a more orderly shutdown of this bus to actually go in and address the fault that occurred here. The 849, if it's installed in a motor bucket, typically it would be used as light sensor as well as the normal motor protection. But because a contactor that would be in the bucket is typically not rated to interrupt short circuits, we would take that flash of light and communicate its detection up to a relay that might be attached to an income or main breaker on the MCC, because that breaker will have the capability of interrupting the fault. And this is something that typically would be done faster than the fuse's response would be for that arc flash. Here's a picture of the 849 installed in not a traditional bucket, but an outdoor control cabinet. And you can see in a case like this, it's been considered. Look at the little lens right here. You can see the 849 is positioned at the top of the cabinet, and it's able to see a flash of light that comes from any place down below it. And over this Ethernet cable here, it could communicate out to the upstream main relay that it has detected a flash of light and request if the main relay sees that this guy has seen a flash of light and it itself sees the current from the fault, it'll know to go ahead and clear the MCC. So I hope that you guys are intrigued by it and thinking that this sounds like a great idea, but probably also asking yourself, does it work? Do people really use this? And so for that question, if you're like me, you would be asking that question. We do have some slides showing a few real events that have occurred. What you see before you here is a picture of some switchgear that suffered an arc flash event. In fact, we can see the perpetrator right here. So this arc flash event occurred because of this rat. This is not what animals usually look like after they've caused a fault. And this is not what switchgear usually looks like after it's suffered through an arc flash fault. This was an 8,000 amp fault. As you can see, there's some evidence of the fault, but there's not really any significant damage. This is to the point that you could take it out of service, clean it up, put it back in service. We're not rebuilding the switchgear. We're not having difficult conversations with our personnel and their families. This event, arc flash detection, saved us a lot on this event. We can see from the event report that was captured by the relay that right about here, where the short circuit begins, before we even make a full cycle, before we even make a half cycle or a quarter of a cycle, we've detected the overcurrent condition and we've detected the flash of light condition. And we're really just looking at the breaker operate time for the rest of this. 2.5 cycle duration. Just to remind you from earlier in the presentation, Gotham showed you this exact same picture. This is what it would have looked like if we hadn't done anything, right? This is what can happen to your switchgear. Hopefully there were no people present for this, but even if there weren't, this is still a devastating loss in terms of downtime and cost for your facility. Here's another example that we saw from a generation station. Again, you can see the duration is pretty much down to just the breaker operating time, just a slightly slower breaker there. Of course, we've got a lot of resources for this. Gotham and I are part of your resources, but we also have a full team of application engineers across the nation who would love to talk with any of you guys about this technology, give you guidance on how to apply it. And we've got a good bit of documentation available on our website as well. Anything from generically how the technology works and how you apply it to specific cases, or you might have to make slight adjustments to the application. The case I mentioned where the 849 would communicate to an upstream device, and even how to test it. So with that, we've kind of reached the end of our part of this. I think the conclusions that you can draw are fairly obvious. We know this is something that we have to deal with, but because of the relaying that we have in place and because of technology that's currently available, we can take fairly non-drastic measures to improve what would otherwise be a drastic failure. And so with that, if you guys have any questions, Gotham and I are here and ready to answer them. And again, excited to be here and present this technology with you guys.
All right, thanks very much, Jeremy. Thanks, Gotham. I'm just going to jump over to another screen here where I'm going to reshare how you guys can ask those questions. So you'd be looking at, again, Pete's portrait here with the location of the Q&A box. So if you have any questions, please reach out, put them in here. Jeremy, I was really shocked by the number of incidents that Gotham told us about at the beginning of this. One death a day due to arc flash just blew my mind, actually.
Yeah, it's easy to forget how much industry is really going on in our nation, and how much industry there is, how much maintenance work there is, how much risk and exposure there is. There's a lot of opportunity for it not to happen to me, right? So oh, that's somebody else. It won't happen to me.
Yes.
But when we see those numbers, we're kind of reminded that it wasn't going to happen to those guys either, but then it did.
Right. Yeah, exactly.
We know we have to take this seriously.
Yeah. And to your point is, you can imagine how many incidents there are where, which you're causing damage to equipment and other things. So like you say, minimizing that, must be fairly crucial. So just a few questions right now. First off, we've got many companies advertise arc flash compliance. What do they mean by compliant, and who governs it?
Yeah, compliance is always a tricky term, right? And some people do advertise just a vague word, compliance. We try to be really careful at SEL with throwing that word around. There's a lot of standards that we build products to adhere to apply to, but typically compliance to a standard employs a lot more than just one product off the shelf, right? So, in fact, NFP 70E, those standards like those don't tell you how to be arc flash compliant. They tell you how to deal with arc flash. Being arc flash compliant implies, or at least being compliant with those standards, imply that you've recognized the risk, that you've appropriately calculated the magnitude of the risk, and that you are giving your employees and your facilities the equipment and the practices, the various controls that Gotham mentioned. Anything from hazard elimination, process controls, engineering controls, and PPE to appropriately protect themselves from those hazards.
Right. Cool. So next up is, what technology is used for the light sensor to meet the required response speeds?
So it's real simple. It's really just a piece of clear plastic that lets light in, and it travels. That light, there's so much light. I mean, Gotham shared with you the temperature. You can imagine the amount of light that goes along with that temperature, that amount of energy. There's so much light that almost any way you point the lens, we're going to get some of it in. It's going to bounce around inside the walls of that clear fiber and make its way into the jacketed fiber. And literally, we're just using typical fiber transceivers and receivers like you would use in a fiber Ethernet port or a fiber serial port to receive that light and to say that we see some signal or we don't.
Right. Okay. Excellent. So, all right. And the last one here is, are you guys used much in the way of ATEX or EXP, EXD junction boxes?
I'll be honest with you, I'm not familiar with that specific standard. I'm inferring that that's what we're asking. A junction box is built to an ATEX or EPX standard.
Yes. Yeah. So I think there's EXD would be flame proof, EXP would be purged.
Okay. I do know, and it varies by product, but we do have various hazardous environment certifications. All the products are actually built just about the same, to the same standards and the same rigor. But on some specific products, we know that they are applied and have to be applied to some of those standards. And so we do the additional testing to confirm that they meet. those standards. So that question would best be asked to a specific application, but that's something that we're happy to follow up with. The customer asking the question, I'd love to be able to follow up with and find out if exactly what qualifications they need for the product, and we can find out if we meet those. Additionally, any case where we don't have that listed specifically to the relay itself, we also have a custom enclosures group at SEL that could help build an enclosure for relaying or any of our other products, so that enclosure together could help meet those standards.
Right. Okay. So somebody can come to you with just a general specification on what their needs are, and then you guys will work with them on not just your product, but even the full sort of enclosure surrounding that.
Yeah, at SEL, we have a lot of different layers of service available. So we have that custom enclosures group. We also have an engineering services division. And so Gotham and I, we're the application engineers. We're what I like to call the free support, where our job is to educate. We make sure our customers have all the information they need. We teach our customers how to use our products. When we get to the level of needing to work with you specifically on a product, you need engineered deliverables from SEL. We can provide that through our engineering services division. And if you have a spec for construction of a cabinet, or if you would like engineering services to design a cabinet and have SEL build and deliver it, that we can offer that through our custom enclosures group.
Right. All right. Thanks, Jeremy. And thank you, Gotham. I want to thank you guys, SEL, and all of the other presenters that are on. I still see Jeff on, obviously getting some of the information from you guys today. So thanks everybody for that. I want to thank all the attendees for joining us today in the Automation Village breakout sessions. And I want to remind people that we do have another Automation Village session. This is going to be more like our first session. So it's going to be sort of a little bit more fast and furious, in that we'll have short presentations and have many presentations kind of back to back to back. And so if you're interested in that, that will be happening Thursday, April 23rd from 10 a.m. to 1 p.m. Eastern. And like these presentations have been, there's no cost to these. So if you'd like to join in one of those, then please feel free to head to the VT SCADA website or look for the email from Natasha to sign up. Thanks very much to everybody who attended. Again, look for our next webinar next week. It's going to be, again, the sort of fast and furious pace of the Automation Village. It'll basically be a 10-minute presentation, and there'll be back to back to back to back with small little intermissions and different content coming in from all sorts of different sources. There'll just be one track for that. So they say as it's a little bit of a mixed industry, but generally very interesting topics for people coming from all kinds of different industries. So thanks very much, everybody. I hope you guys have a wonderful day, and please stay safe.